Hi, I'm Connor, and today we're going to be discussing the USACO December 2022 Silver Problem 1 Barn Tree. In this problem, we're given a graph with n minus 1 or n nodes and n minus 1 edges, and we want to see what's the minimum number of moves if we can transfer some amount of hay from one barn to an adjacent barn. What's the minimum number of moves that it takes to make all the amounts of hay in each barn equal? So, for instance, in this graph, we have a total of 12. We have 4 nodes and 12 hay bales between them. So, we have to try and get 3 hay bales to each barn. So, one way we can do this is we can first move 1 hay bale out of there, which turns that into 3, and this into 2. Then we can move 2 hay bales out of here, which turns this into 3. And then this goes into 4. And then we can move 1 hay bale up there, turning this into 3, and turning this into 3. And now all of the nodes in this graph, or all of the barns, have 3 hay bales in them. So, and this took a total of 3 moves, which is the minimum. The first thing to notice with this problem is that it is a graph problem, where we're given some nodes, which are the barns, and some edges, which are the roads between the barns. And in fact, this is a special case of a graph problem, where we're actually given a tree, as implied in the problem name. A tree is a special kind of graph, where if a graph has n nodes, if it has n minus 1 edges, then that makes it a tree, as long as it's connected, which is a special kind of graph that has no cycles. So there is only one way to get from any one node to another, at least in the minimum amount of moves. So one special thing you can do with trees is something called tree DP. Tree DP is an algorithm which makes use of the fact that essentially the subtree of any tree is a tree in and of itself. So, for instance, this part of the tree is a subtree of the whole tree, and this part of the tree is also a tree, because we see that this has 3 nodes and 2 edges if we ignore this one that's going out. And tree GP basically makes use of this fact by essentially calculating the answer for every smaller subtree. So it first calculates the answer for like just that node 4, and then it calculates the answer for this node 3, and then it calculates the answer for this whole subtree here by combining the answers it got for the subtree at 3 and 4, and then combining it with the parent node of 2. And it does it again for the entire tree, which gives you the answer at the end. So tree DP is a really convenient way of solving tree problems, because it's very simple to write as well. Essentially, you just make a recursive algorithm that recursively solves the problem for every subtree of a node. So for instance, if we're at node 2, then you can recursively solve it for node 3, and recursively solve it for node 4, and then go back to node 2 to combine the solutions. Before we talk about how tree DP applies to this problem, let's look at one way to make this problem more convenient for us. So in this problem, we want to get every barn to have the same amount of hay bales at the end. But notice that we actually know how many hay bales we want at the very start before we even do any calculations. This is because we want every barn to have the same number of hay bales. So if we take the sum of the hay bales, and then divide it by the number of barns, that gives us the number of hay bales we have to put in each barn. So we already know at the start how many hay bales we need in each barn. And one kind of thing we're going to do to make this a little easier for us to calculate the answer is to actually turn these numbers of absolute hay bales into relative number of hay bales. How many too many it does it have, or how many too few does it have? And we can do this by just subtracting the number of hay bales per barn from the original number. So for instance, if in our sample input here, we're meant to get 3 hay bales per barn, since there are a total of 12 and there are 4 barns. So if we subtract 3 from every one of the nodes, then what do we get? We get 1 here, we get 2 here, we get -2 here, and we get -1 here. And the cool thing here is you can see actually if each barn has too few or too many barns just at a glance, or too many hay bales just at a glance. Because we see that these positive numbers mean that we have more hay bales in this barn than we should. So if we have a positive number, then we know we want to get rid of some hay bales in that barn. And if we have a negative number, then we know that we have fewer hay bales than we should. So then we know that we want to give that barn some more hay bales. Let's do a small example of a subtree here. So in this case, we're looking at this node right here, and this node has -1 hay bales, and these are the normalized numbers, so it has 1 less hay bales than it should. And it has these 4 children down here, which have varying numbers of hay bales each. So we want to try and distribute these hay bales so that all of these children and this one have 0. And note that we don't have exactly enough hay bales to do this. We might end up with some extra. So those extra ones will just send off the tree to its parent, where it can go into some other subtree that's maybe missing some hay bales. So let's look at these nodes. So in this child here, we have -4 hay bales. So it needs 4 extra hay bales from somewhere, but we don't have any in this tree right now. And same for this -6. We need 6 more hay bales from somewhere, and this node right there doesn't have the supply for that. So we have to get that supply from somewhere else. And luckily we have 2 extra nodes here, and these 2 extra nodes are going to need to move their extra hay bales out of the subtree, or out of this child. So we can start with doing those operations. So we can move some of the hay bales up there, and that'll give us that'll move 8 hay bales out of there, so that goes to 0. And then we end up with 7 extra hay bales there. And then same thing for this 5 one. We have 5 extra hay bales for that child, so we can transfer 5 hay bales out of it, and then put it into this one, which gives us a total of 12 hay bales in there. So, and then we can use those 12 hay bales to now give to those children that are lacking of hay bales. So we can give 4 hay bales to this child. Get rid of that arrow. You can give 4 hay bales to that child, in this instance 0, and then that brings it up to 0. So now it has enough hay bales. And we can give 6 to this child, so that gets set to 0. And since we gave away 10 hay bales, this now has 2 extra hay bales. And then those 2 extra hay bales, since this is just a subtree of a larger tree, there's probably some more nodes up there, we'll want to send those out of this tree. So we send 2 hay bales away, and now we're left with 0. So this subtree here is entirely equalized. So that's just one example of one subtree that we could potentially do to make it all have the correct number of hay bales in each barn. Let's do another example. So in this subtree, similarly, we are looking at this node right here, and we want to redistribute everything so that all the nodes end up with 0 hay bales, so they have exactly the amount they need. So once again, we can start with this one node here, since it has an extra hay bale, so we can transfer that up there, and then this turns into a -1. But this time there's an issue. We don't actually have enough hay bales in this subtree that we're able to bring them all to 0. So we need to actually get 6 more hay bales from the parent. And we know that these 6 hay bales will exist because we calculated that there are exactly enough hay bales in all of the nodes to bring them all to 0. So we'll be able to gather these 6 hay bales from some other node somewhere else in the in the tree. So we get those 6 nodes, or we get those 6 extra hay bales, and that brings us up to 5. And then we can distribute those among uh, the other nodes to bring them all to 0. So we send 2 hay bales to this node, and we send 3 hay bales to this node to bring them both to 0. And that brings this down to 0 as well. And the reason we bring in 6 hay bales to this tree is that we were lacking exactly 6 hay bales, because this had -1, this had -2, and this had -3. So we had a net negative of 6 hay bales, so we need to grab those from higher up in the tree. Now the cool thing about tree DP is that these nodes down here don't actually have to just be single nodes. They can actually be entire subtrees as well. And this is the case because we don't really care what happens in these subtrees, as long as we know that we can get some extra hay bales out of them, or we have to send some hay bales to them. And in fact, that's exactly what I've done right here. This subtree here is exactly this node. If I just move it up here, then we can see that this subtree here just fits exactly into this slot here. And we still get the 6 hay bales sent from the upper tree down to the lower tree. And the reason we're able to do this is just because this tree, if we process all its stuff first and we realize that it needs six hay bales, then we can just say that, oh, now this is basically a child where we need exactly 6 hay bales, and then we can get the parents to send that over. So if we process the child first, then we are able to see which nodes need some extra hay bales and which ones have extra hay bales that they are available to send out. And the important thing here is we're able to know that we can send 6 hay bales to this subtree because the sum of all the deficits, this was originally -2, the sum of all the normalized values in here, if we sum this all up, then we get a total of -6. So we can just treat this entire subtree as one giant node that has a value of -6, and we can get the parent to send 6 that way, and then process the subtree. So yeah, so that's the idea of tree DP. We can essentially look at each parent and each child individually, and then only treat them as subtrees when we want to. Let's get a better idea of how our solution is going to work with an example. So we have our entire tree here, and we have all our normalized values. You can check that all of these values do add up to 0. So we want to try and get all the values in this tree to be equal to 0. So we start off at this root node here at the very top, and we want to try and equalize it and its subtrees. So right now, it has 2 essentially subnodes, and each of these either needs some hay bales or has extra hay bales. So if we look at this one, this entire subtree right here, if we sum up all the hay bale costs, or all the hay bale needs, it needs an extra 2 hay bales, since this entire subtree sums up to -2. So this way, we need to send 2 hay bales to this subtree eventually, but we don't have those 2 hay bales to send it yet. So first, we can look at this subtree here, and this subtree has a sum of 3, which means it has 3 extra hay bales that it has to send out. So we want to look at this subtree first and try and get it to send out 3 of the hay bales. So when we look at this subtree, well, before we can get it to send the hay bales, we have to actually look at what the subtree is doing and transfer the hay bales around. Because if we just tried and send it immediately, we can't send 3 hay bales from this node to this node because this node doesn't have 3 hay bales yet. So we have to process the subtree first. So now our new root is going to be this one. So looking at this tree, we have a similar thing where this node here has -1 hay bales. So we have to send that 1 hay bale eventually. and this one has 3 hay bales. So we can just immediately go and, well, technically we go down and operate on this tree. Uh, but all we're doing there is we're just sending the 3 hay bales up to this node. Because technically this single node is also a subtree, so we need to calculate that first. So we send all these 3 hay bales up there, and now we're left with 0, which is exactly what we want. And now at this one we have 4 hay bales, which is too many. So now we can finally equalize this one. So we send 1 hay bale that way, and we get left with 0 there, and we get left with 3 here. And then finally, we're able to send the 3 extra hay bales back up to the root node. So now we're looking at this one again, and it has 2 hay bales there. So since this other subtree is missing 2 hay bales, we can just go ahead and send those down there, and then that puts us at 0. And now we can operate on this subtree. So, okay, so now this subtree has a total of 1 hay bale there, or at least that node does. And we can do a similar thing where we look at the positive subtrees, and then we send the hay bales up from there. So this becomes 0 and this becomes 2. And then we can send the hay bales down there. So we send 2 hay bales down there. This becomes 0, and then this becomes 0. So now we can see all the operations that we did. We sent some hay bales up the tree to get to the other side. Meanwhile, we sent some other hay bales down the tree so that we're able to equalize those subtrees. So yeah, and this is actually the minimum solution possible. You can see that we only send hay bales along a route once, and this is the minimum possible, since if you think of a long tree that's just node after node after node after node, and you have -1 here, 0, 0, 0, 1 here, then we have to send it all the way there. So the minimum number for at least this case is the number of edges. And we can see that in this case, we had to send some up there and then down there. So we do use every edge once. That's not always going to be true. If we had a node there that's already 0, then when we go down there, we see that we don't have to send it anywhere, and we don't have to send anything from it. So we don't actually have an order for that one. And the solution is minimal because one way to see this is that we never use any node twice. We never have to send anything from there to there and from there to there, because that's kind of a waste. If you send 3 hay bales there and 2 hay bales there, then why couldn't we just get rid of this and send 1 there all at once? So yeah, so this solution is minimal because we never use any edge twice. And yeah, so that's our solution. We essentially look at every node, we send some hay bales to a subtree, we receive some hay bales from the subtrees, and then we can redistribute them. A couple things to talk about before I get to my solution code. One is that I mentioned that I looked at the sum of some subtrees before I went into them. I can actually optimize this by pre-calculating the sum of every subtree by doing another recursive search. So essentially I can just look at this subtree, or I can start at the root node, and to find the subtree sum of this node, you can look at the subtree sum of every child node plus the value of the current node. So that's kind of a recursive way to do it. If you look at this one, then the sum of this node is going to be the child, each of the children's sum. So this would be -2 and 1, and then added to this one. So -2 plus 1 plus -1 is going to be equal to -2. And you can kind of recursively do that. And for this node, you only have to actually look at this value. You don't have to ever care about these ones again because they're already accounted for in this sum. So yeah. Also, the time complexity of this solution is O of n. And this is because we look at every node only twice. Once when we're calculating the subtree sum, another one when we're actually recursing in it and doing all the orders. The solution actually has a pretty large runtime. That's probably just because you have to actually store every single order, so that takes a while. Now let's go over the C++ solution code to this problem. So let's start with the main function down here. This part is just reading in the input, so we read in n, we read in all of the values of h, and I keep track of the sum in this variable. You'll note that I use LL here. This is just another way to type long if you do this type def here. This is important. Long is just 64-bit integers, and this is important because this sum can be very large. Every node can have 10 to the 9, and there are up to 10 to the 5 nodes, so that can potentially overflow if you just use normal integers. So beware of that. So once I find the sum, once I read in all of the values of h, I normalize the values, and this is what I talked about. The goal value is equal to the sum divided by the number of nodes. So we just subtract that from every node. And now here I read in all of the edges. Not too much to worry about there. And then I do two different depth first searches. And depth first search is just a way to recursively look at each subtree of the tree. So I do two depth first searches, DFSs. First one is DFS sum, which finds the subtree sum of every subtree. The other one is DFS ord, which just prints out all of the orders, which is what I called the movements of the hay bales. So let's look at this subtree sum DFS first. So that's this function, which finds the subtree sum of every subtree and stores in this array called subtree sum. So if we look at this function, this is generally like the general structure of a DFS. We keep track of a variable with the current sum of this subtree. Now we loop through all of the next nodes in the adjacency list. So an adjacency list is a way to store a graph such that we keep track of all the adjacent nodes. And in this case, for the DFS, we keep track of the current node, which is x. And we also keep track of the parent node so that we don't accidentally go backwards on ourselves when we're doing the recursive. So we loop through over all the adjacent nodes, make sure it's not the parent, and then we recursively find the sum of that subtree. So we find the subtree of the node with root at x, and the parent is now x itself. So then we add that subtree sum to the current sum, and of course if this is a leaf, which is the end of a tree, then we know that there are no adjacent nodes, so current sum is just going to be the value of the leaf itself. So at the very end, we set it to be the subtree sum array, and then we set that to be the current sum, and then we return the current sum. So this is a simple recursive function that just sums out all the values of h in every subtree, and then stores in the subtree sum array. And note that our starting node, we call the function initially with the value 1, so if starting node is 1, it doesn't matter what node you start with, I just generally root the tree at 1, because it's usually simpler that way. So yeah, now we get to the complicated DFS. So this DFS ord function is where we do all the work we talked about previously, where we take all the hay bales, take them from subtrees with too many hay bales, and then redistribute them to subtrees with too few. So we can see that in these three separate steps. In this step 1, we first search over all of the positive subtrees. So we look for all the subtrees with sum that is positive, and then we go to those first because those ones have extra hay bales, and then those subtrees will be able to give the hay bales back to this one. So then we just recursively call the order DFS on the subtree. And we don't really have to worry about it because we're getting sent the hay bales by that subtree. Step 2 is we DFS over all the neutral or negative subtrees, and then we give them hay in the process. So these are the subtrees that have negative value, just like the one with negative 6 value from earlier. So we check to see if subtree sum next is less than or equals to 0. And then we also have to check if it's less than 0, because if it's equal to 0, then we don't have to really care about it. We still have to recursively search that subtree because it might be unequally distributed among that subtree. but we don't have to send anything between the subtrees because um, because it doesn't need any hay and it doesn't need to give away any hay. But if the subtree sum is negative, then it does need some extra hay. So we push back an order into the orders list. And this order type is just a custom structure I made in C++, which stores the source, the destination, and the amount of hay bales. So in this case, the source is x, and it's giving it to the next subtree, and it's giving the negative of the subtree sum, because that way it gives 6 hay bales to a subtree with -6, etc. And then we do the recursive search on them. And it's important that we do in this order. We need to give them the hay first before we actually do the recursion, because we need to make sure that they actually have enough hay to be able to recurse. Note that we don't actually have to change the subtree sum. We just kind of implicitly give it to them and assume that we have enough whenever we're doing this recursive search. And finally, in this last step, it's just we check to see if we have any extra hay, and we can do that by just checking to see if the subtree sum of the current node is greater than 0. And we need to make sure it's not 1. I don't think this is really important, but we don't want to give any extra hay of the root of the tree anywhere. So we just add an order where we give from the source is the current node, and then we give it to the parent, and then we give it equal to the number of extra hay bales in this tree. So that's kind of the recursive search. It does exactly what I described earlier, where it redistributes all the hay bales and puts that in the orders list. And finally, once we're done with that, then we print out all the orders. Pretty simply, just loop through all the orders array and remember to print out the size at the start. And yeah, so that's about it for the solution. And that's about it for the problem overall. Thank you for watching.